Hello, everyone. It's a pleasure to present our work at this talk. My name is Nguyen, and I come from China. I am a student at Institute of Computing Technology, Chinese Academic of Sciences. Professor Zhang is my mentor, and this work is under his guidance. Li Xinyu is a student too. We both work in the binary translation area. This is the content that I will discuss about today. First, I will give some background about binary translation. Then I will introduce the basic interrupt tracking scheme and explain why it is inefficient. Then I will introduce the design and implementation of our scheme. The evaluation is split into three parts: the performance, the interrupt latency, and some profiling results to analyze the speed up. I will end with the conclusion and then start the question and answer. Okay, now we start with the background. Dynamic binary translator is a technique that can run cross-ISA programs. The guest program's binary code will be translated to the host binary code, which can run on the host platform directly. For example, the guest can be x86 and the host can be ARM. There are many binary translators like QEMU, Intel's Houdini, Apple's Rosetta, and the famous Transmitter. There are two types of them. The user mode dynamic binary translator can run user space programs, and the full system translator can run a complete operating system. How does the binary translation do this? Here is a simple example of binary translation. The guest is x86 and the host can be any other ISA. The guest CPU state is stored in memory. For the guest add instruction, we can generate the following instructions to emulate its function. The register's value is read from the memory and the add operation is performed. Then the results will be stored back to the memory. Multiple guest instructions can be translated together to form a translated block. The execution of guest is emulated by the execution of translated blocks. Since the translation is time-consuming, we can save the translated blocks to avoid translating it again. If the next block doesn't exist, the binary translation will be invoked to generate the next block. Here is a basic optimization, block chaining. In this example, block A ends with a guest instruction, which is a direct jump. After executing the block A, the translator will look up for the next block to execute. Once the block B is generated, we can modify the host instruction inside the block A to make it directly jump to block B. Then the context switch, the lookup, will no longer be needed. The thread that executes the blocks is named vCPU thread. In the full system dynamic binary translator, there is usually another thread that helps the emulation of devices. The thread can send an interrupt to the vCPU thread. The vCPU thread should emulate the behavior when the guest CPU receives an interrupt. For example, when the guest is x86, the vCPU thread should look up the IDT tables to find the entry of the interrupt handler. How does the vCPU thread check the pending interrupts? Here is the basic interrupt checking scheme. A piece of interrupt checking code is patched at the beginning of every translated block. In this example, an interrupt occurs when the vCPU is executed inside the block A. Then it will execute the block B, and it will note there is a pending interrupt. Then the block B will not be executed, and the execution flow will be redirected to the context switch. After the context switch, the interrupt will be handled by the dynamic binary translator. But the interrupt is a rare event compared to the execution of translator blocks. Here is a simple profiling result of interrupt checks. We collect this data with a global counter. If one interrupt check reports there is no pending interrupt, the counter is increased by 1. Otherwise, we record the value of the counter and reset the counter to 0. The larger the number is, the more time is wasted on interrupt checking. According to the result shown in the chart, it is obvious that many time is wasted on these unnecessary interrupt checks. Our idea is simple. We can inform the vCPU thread when the interrupt should be delivered to avoid the repeated interrupt checks. There are 2 challenges. First, when an interrupt is delivered, the vCPU thread should stop executing blocks and go to handle the interrupt. Second, when the guest has more than one CPU core, there will be more than one vCPU thread. The synchronization between them should be carefully maintained. For the first one, we can perform the unlink operation on the translated block that is currently executing. After that, the execution flow will be redirected to context switch. Then the dynamic binary translator will check and handle the interrupt after context switching. On the opposite, the relink operation will resume the block link relationship to avoid further performance loss. There are various situations when the vCPU thread receives a signal. We need to find the block that is currently executing. For situation A, the vCPU thread is not executing blocks, so the signal handler could simply do nothing. Well, more details will be described in the paper. And for situation B, the vCPU thread is running inside the helper function, which is called from a translated block. We will store the pointer of this block into memory before calling the helper. Then inside the signal handler, we could get the pointer and unlink it. For situation C and D, we need to search for the blocks with the PC provided by the signal handler. Well, searching can be time-consuming. For the second challenge, when there are more than one vCPU threads, usually the block cache is shared by this vCPU thread so that there will be no redundant translation when different vCPU threads are executing the same program. But it allows different vCPU threads to modify the same translated block. In this simple example, the vCPU1 and the vCPU2 are executing the same block. At the time B, this block should be unlinked for vCPU2, but it is relinked by vCPU1. This is not right. Our solution is simple. First, the unlink and relink operation should be protected by the lock, since they could be modifying the same block at the same time. Second, we only allowed the last vCPU thread which unlink this block to perform the relink operation. Each vCPU thread that unlink this block will mark this block with its thread ID. So at step 2, the vCPU thread will not do the unlink operation because it knows there is another thread that already unlinked it. And at step 3, the vCPU1 will not do the relink work because it knows there is another vCPU thread still need the block to be unlinked. The vCPU1 only set its thread ID and clear its thread ID. Then at step 4, the vCPU2 knows he is the last vCPU thread, so it will relink this block. Well, for the evaluation, let me introduce the setup first. We evaluate our scheme with latex, which is a full-system dynamic binary translator based on QMU. It can run x86 on long arc, which is an instruction set architecture designed by Longshan. The host platform is a 3500 CPU running with the Linux kernel 4.19, and the guest platform is x86 Ubuntu 16.04 with Linux kernel 4.4. The benchmarks we chose is SPEC CPU2000 integer benchmarks, and the two micro benchmarks, CoreMark and HD Palmer. The baseline is latex without our scheme. First, the performance. We do the evaluation with different block size. When the block size becomes smaller, the number of the blocks will increase, since our scheme removes all the interrupt checking codes from every block, so the speed up will be larger. According to the results, the speed up is up to 48%. With normal block size, the CPU-bound benchmark speed up is about 3%, and the I/O-bound benchmark shows no speed up and no slowdown. Then we evaluate the interrupt latency. Our scheme introduces extra overhead on the interrupt latency delivery. We identify 3 time points to calculate the interrupt latency. The T-send is the time when an interrupt is delivered. The T-execute is the time when vCPU starts to handle the interrupt. This could be a complex work. For example, when the guest is x86, it needs to look up the IDT tables to find the entry of the interrupt handler. It needs to do some context-rich work. And the time down is the time when vCPU threads finish handling and gets ready to execute the guest's interrupt handler. Well, in general, the latency sent to execute is the latency seen by the dynamic binary translator, and the latency sent to down is the latency seen by the guest. On average, with default block size, the send to execute latency is increased by 13%, and the send to down latency is increased by 20%. Then we do further evaluation on the interrupt latency. On the left chart shows the different situations met by the signal handler. In 67% cases, the signal handler needs to search for the block. In 24% cases, it only needs to unlink the helper block. In the remaining 9% cases, it can simply do nothing. Well, the signal handler's overhead mostly comes from searching the blocks. When the block size goes smaller, the number of blocks will increase. The red chart shows the send-to-execute latency with different block size. We can see that when the block size is limited to 1, the extra overhead is only 14%. Well, does the increased interrupt latency harm the overall performance? We performed the sensitive test on two macro benchmarks. We manually increased the overhead of the signal handler. According to the result, when the send-to-execute latency is doubled, the slowdown is only less than 1%, while our scheme only introduced 13% overhead on the interrupt latency. Finally, we are trying to figure out where does the performance improvement comes from. First, we collect some data with the Linux perf tool. The number of branch instructions is reduced by 11% on average, and the number of cache access is reduced by 5% on average. This is reasonable because the interrupt checking codes contains a load instruction and a bridge instruction, and they are all removed by our scheme. Then we manually add more instructions into the original interrupt checking codes and evaluate its influence. We perform this evaluation on 2 different host platforms. The performance slowdown mostly comes from the branch instructions. So we could conclude from the above that the speed up mostly comes from the removing of the branch instructions. In this paper, we propose a novel and efficient interrupt checking scheme for a full-system dynamic binary translator. Our scheme removes the interrupt checking code from all the translated blocks, which results in an overall performance speed-up. We utilize the signal to inform the vCPU thread to avoid the repeated checks. The interrupt latency does increase, but it does not harm the overall performance. And recently, there is a new technique named user space interrupt, which is much more faster than the unique signal. It could be applied to further reduce the overhead of the interrupt latency. Okay, that's all we would like to share at this meeting, and thanks for listening.
Hello, thanks for the talk. Some of the performance benefits stems from a reduced number of cache misses, and I assume you measured the cache misses by reading the performance monitoring counters. Are these code or data cache misses?
It's the data cache misses.
Anyone else want to try asking a question?
Okay, so let's thank Jen again.